Pulleys are cool because they allow us to change the direction of a force. So what we have to think, instead of thinking like left, right, up, or down, we're going to think about the direction of motion. So basically the direction of motion is like this. That is our direction of motion. We know it's going to travel in this direction. I'm going to call this the positive direction because 5 kilograms is bigger than 2 kilograms. Obviously, it's going to go clockwise around that pulley. So I'm going to call this one 1 and this one 2. So basically what we can see here is that we're going to have our F net is equal to mass times acceleration. That's equal to the applied minus the opposed forces. Applied forces minus the opposed forces. So in this case, though, we think of it as like it's going this direction. So the 5 kilograms is making it go that way. So that's our 5. The force of gravity from the 5 kilograms is going to be our. There's our force of gravity. That's going to be our Fg. We're going to call it Fg2. This is going to be our Fg1. So Fg1 is making this thing accelerate. Fg2 is making this accelerate. Fg1 is opposing that acceleration. At the same time, there's going to be this tension force. They're going to be equal and opposite. So when I write out my equation for this one, I'm going to say F net is equal to MA. So what's making this thing accelerate is Fg2. But if I just kind of trace this backwards, I start with Fg2. This clockwise direction is positive, so Fg2 is pointing in the clockwise direction, so I wrote it as positive. This tension right here, minus tension. This other tension, it's in the direction of the arrow, so plus tension. And minus Fg1. So again, those middle forces, it's cancel out because right now I'm looking at the thing as a whole right now. So that's with MA is equal to Fg2 minus Fg1. Now you're saying, what is this M over here? What is that M? That is the whole system. This is like my total mass. Basically, like Fg2 is making the whole system accelerate. Fg1 is opposing that acceleration. What is actually accelerating? The whole 7.0 kilograms. And the 7.0 kilograms. All those 7.0 kilograms are being accelerated by some quantity. So I have 7.0 kilograms times A, and that's equal to 5.0 kilograms times G minus 2.0 kilograms times G. So we solve for A. We have a value of 4.2 meters per second squared. So to solve for the next part, again, we're going to do exactly what we did in the previous question. We have to look at one of the blocks individually. So for example, if I look at that 2 kilogram block, here's just the 2 kilogram block, 2.0 kilograms. We know it has Fg1 going downwards, but there's also that tension force going up. So I should actually be drawing that tension force bigger than Fg1 because we know this thing's, for Fg1 it's accelerating upwards. Fg2 on the other hand is accelerating downwards. So it doesn't matter which one we do. I can look at, if I looked at the other one, it'd be Fg2. And there's my tension going up. For this one, the acceleration is up. For this one, the acceleration is down. So when I write this one, I say, okay, this is M1A is equal to tension minus force of gravity 1. So tension is equal to M1A plus M1G. And we just solve for acceleration is 4.2. So we go 4.2 times our mass, which is the 2 kilogram mass, plus 9.81 times our 2 kilogram mass. We get a force of 28 newtons. To look at this other one, though, I can say, oh, M2A is equal to, oh, it's going downwards. So I can say down is positive, so I have Fg2 minus tension. So I can see that tension is equal to Fg2 minus M2A. So this one I have a 5 kilogram block times 9.81 minus 5 kilogram times that 4.2. And guess what? We get the exact same force, because I know that if I solve for one, I solve for the other as well, because Newton's third law states for a reaction, which is equal and opposite reaction. So if one end of the rope feels the force of 28 newtons, the other end of the rope must also feel force of 28 newtons.